Chapter 9 Differential Equations. Introduction. For a given function g, find a function f such that dy by dx is equal to g of x, where y is equal to f of x. Equation 1. An equation of the form 1 is known as a differential equation. A formal definition will be given later. These equations arise in a variety of applications. May it be in physics, chemistry, biology, anthropology, geology, economics, etc. Hence, an in-depth study of differential equations has assumed prime importance in all modern scientific investigation. Basic concepts. We are already familiar with the equations of the type x square minus 3x plus 3 is equal to 0. Equation 1. Sin x plus cos x is equal to 0. Equation 2. X plus y is equal to 7. Equation 3. Let us consider the equation x dy by dx plus y is equal to 0. Equation 4. We see that equations 1, 2 and 3 involve independent and or dependent variable, that is variables only, but equation 4 involves variables as well as derivative of the dependent variable y with respect to the independent variable x. Such an equation is called a differential equation. In general, an equation involving derivative, that is derivatives of the dependent variable with respect to independent variable, that is variables, is called a differential equation. A differential equation involving derivatives of the dependent variable with respect to only one independent variable is called an ordinary differential equation. For example, 2d square y by dx square plus dy by dx whole cube is equal to 0 is an ordinary differential equation. Equation 5. Of course, there are differential equations involving derivatives with respect to more than one independent variables called partial differential equations. But at this stage, we shall confine ourselves to the study of ordinary differential equations only. Now onward, we will use the term differential equation for ordinary differential equation. Order of a differential equation. Order of a differential equation is defined as the order of the highest order derivative of the dependent variable with respect to the independent variable involved in the given differential equation. Consider the following differential equations. dy by dx is equal to e raised to x. Equation 6. d square y by dx square plus y is equal to 0. Equation 7. d cube y by dx cube plus x square d square y by dx square whole cube is equal to 0. Equation 8. The equations 6, 7 and 8 involve the highest derivative of first, second and third order respectively. Therefore, the order of these equations are 1, 2 and 3 respectively. Degree of a differential equation. To study the degree of a differential equation, the key point is that the differential equation must be a polynomial equation in derivatives, that is y dash, y double dash, y triple dash, etc. Consider the following differential equations. d cube y by dx cube plus 2 d square y by dx square whole square minus dy by dx plus y is equal to 0. Equation 9. dy by dx whole square plus dy by dx minus sin square y is equal to 0. Equation 10. dy by dx plus sin dy by dx is equal to 0. Equation 11. We observe that equation 9 is a polynomial equation in y triple dash, y double dash and y dash. Equation 10 is a polynomial equation in y dash, not a polynomial in y though. Degree of such differential equations can be defined, but equation 11 is not a polynomial equation in y dash and a degree of such a differential equation cannot be defined. By the degree of a differential equation when it is a polynomial equation in derivatives, we mean the highest power, that is positive integral index of the highest order derivative involved in the given differential equation. In view of the above definition, one may observe that differential equations 6, 7, 8 and 9 each are of degree 1. Equation 10 is of degree 2, while the degree of differential equation 11 is not defined. Example 1. Determine order and degree if defined of differential equations. Number 1. d raised to 4y by dx raised to 4 plus sin y triple dash is equal to 0. The order of the given differential equation is 4 and its degree is not defined. Number 2. Y dash plus 5y is equal to 0. The order of the given differential equation is 1 and its degree is 1. Number 3. ds by dt whole raised to 4 plus 3s d square s by dt square is equal to 0. The order of the given differential equation is 2 and its degree is 1. Number 4. Y dash plus y is equal to e raised to x. The order of the given differential equation is 1 and its degree is also 1. Number 5. Y double dash plus 2y dash plus sin y is equal to 0. The order of the given differential equation is 2 and its degree is 1. General and particular solutions of a differential equation. X square plus 1 is equal to 0. Equation 1. Sin square x minus cos x is equal to 0. Equation 2. Solution of equations 1 and 2 are numbers, real or complex, that will satisfy the given equation, that is, when that number is substituted for the unknown x in the given equation. Left hand side becomes equal to the right hand side. Now, consider the differential equation d square y by dx square plus y is equal to 0. Equation 3. In contrast to the first two equations, the solution of this differential equation is a function phi that will satisfy it. That is, when the function phi is substituted for the unknown y, which is dependent variable in the given differential equation, left hand side becomes equal to right hand side. The curve y is equal to phi of x is called the solution curve, that is integral curve of the given differential equation. Consider the function given by y is equal to phi of x is equal to a sin x plus b, where a, b belongs to R. Equation 4. When this function and its derivative are substituted in equation 3, left hand side is equal to right hand side. So it is a solution of the differential equation 3. Let a and b be given some particular values. Say a is equal to 2 and b is equal to pi by 4. Then we get a function y is equal to phi 1 of x is equal to 2 sin x plus pi by 4. Equation 5. When this function and its derivative are substituted in equation 3, again left hand side is equal to right hand side. Therefore, phi 1 is also a solution of equation 3. Function phi consists of two arbitrary constants, that is parameters a, b, and it is called general solution of the given differential equation, whereas function phi 1 contains no arbitrary constants but only the particular values of the parameters a and b, and hence is called a particular solution of the given differential equation. The solution which contains arbitrary constants is called the general solution, that is primitive of the differential equation. The solution free from arbitrary constants, that is the solution obtained from the general solution by giving particular values to the arbitrary constants, is called a particular solution of the differential equation. Example 1. Verify that the given functions, that is explicit or implicit, is a solution of the corresponding differential equation. Number 1. Y is equal to x square plus 2x plus c. Y dash minus 2x minus 2 is equal to 0. Solution. Y is equal to x square plus 2x plus c. Differentiating with respect to x, we get, therefore y dash is equal to 2x plus 2. Therefore y dash minus 2x minus 2 is equal to 0. Therefore y is equal to x square plus 2x plus c is a solution of y dash minus 2x minus 2 is equal to 0. Number 2. Y is equal to cos x plus c. Y dash plus sin x is equal to 0. Solution. Y is equal to cos x plus c. Differentiating with respect to x, we get dy by dx is equal to minus sin x. Therefore y dash plus sin x is equal to 0. Therefore y is equal to cos x plus c is a solution of y dash plus sin x is equal to 0. Number 3. Xy is equal to log y plus c. Y dash is equal to y square upon 1 minus xy, where xy is not equal to 1. Solution. Xy is equal to log y plus c. Differentiating with respect to x, we get xy dash plus y is equal to 1 upon y into y dash. Therefore y into xy dash plus y is equal to y dash. Therefore xy y dash plus y square is equal to y dash. Therefore y square is equal to y dash minus xy y dash. Therefore y dash into 1 minus xy is equal to y square. Therefore y dash is equal to y square upon 1 minus xy. Therefore xy is equal to log y plus c is a solution of y dash is equal to y square upon 1 minus xy. Formation of a differential equation whose general solution is given. We know that the equation x square plus y square plus 2x minus 4y plus 4 is equal to 0. Equation 1 represents a circle having center at minus 1, 2 and radius 1 unit. Differentiating equation 1 with respect to x, we get dy by dx is equal to x plus 1 upon 2 minus y, where y is not equal to 2. Equation 2, which is a differential equation. You will find later on that this equation represents the family of circles and one member of the family is the circle given in equation 1. Let us consider the equation x square plus y square is equal to r square. Equation 3. By giving different values to r, we get different members of the family. For example, x square plus y square is equal to 1, x square plus y square is equal to 4, x square plus y square is equal to 9, etc. Thus, equation 3 represents a family of concentric circles centered at the origin and having different radii. We are interested in finding a differential equation that is satisfied by each member of the family. The differential equation must be free from r because r is different for different members of the family. This equation is obtained by differentiating equation 3 with respect to x, that is 2x plus 2y dy by dx is equal to 0 or x plus y dy by dx is equal to 0. Equation 4, which represents the family of concentric circles given by equation 3. Again, let us consider the equation y is equal to mx plus c. Equation 5. By giving different values to the parameters m and c, we get different members of the family. For example, y is equal to x, where m is equal to 1, c is equal to 0. Y is equal to square root of 3x, where m is equal to root 3, c is equal to 0. Y is equal to x plus 1, where m is equal to 1, c is equal to 1. Y is equal to minus x, where m is equal to minus 1, c is equal to 0. Y is equal to minus x minus 1, where m is equal to minus 1, c is equal to minus 1. Thus, equation 5 represents the family of straight lines, where m, c are parameters. We are now interested in finding a differential equation that is satisfied by each member of the family. Further, the equation must be free from M and C because M and C are different for different members of the family. This is obtained by differentiating equation 5 with respect to x. Successively we get dy by dx is equal to m and d square y by dx square is equal to 0. Equation 6. The equation 6 represents the family of straight lines given by equation 5. Note that equations 3 and 5 are the general solutions of equations 4 and 6 respectively. Procedure to form a differential equation that will represent a given family of curves. A. If the given family f1 of curves depends on only one parameter, then it is represented by an equation of the form f1 of x, y, a is equal to 0. Equation 1. For example, the family of parabolas y square is equal to ax can be represented by an equation of the form f of x, y, a, where y square is equal to ax. Differentiating equation 1 with respect to x, we get an equation involving y dash, y, x and a. That is, g of x, y, y dash, a is equal to 0. Equation 2. The required differential equation is then obtained by eliminating a from equation 1 and 2 as f of x, y, y dash is equal to 0. Equation 3. B. If the given family f2 of curves depends on the parameters a, b, c, then it is represented by an equation of the form f2 of x, y, a, b is equal to 0. Equation 4. Differentiating equation 4 with respect to x, we get an equation involving y dash, x, y, a, b. That is, g of x, y, y dash, a, b is equal to 0. Equation 5. But it is not possible to eliminate two parameters a and b from the two equations, and so we need a third equation. This equation is obtained by differentiating equation 5 with respect to x to obtain a relation of the form h of x, y, y dash, y double dash, a, b is equal to 0. Equation 6. The required differential equation is then obtained by eliminating a and b from equations 4, 5 and 6 as f of x, y, y dash, y double dash is equal to 0. Equation 7. Example 1. Form the differential equation of the family of circles touching the y-axis at origin. Solution. Let the center of the circle touching the y-axis at origin is C, A, 0. Therefore, radius r is equal to a. Therefore, equation of circle x minus a whole square plus y minus 0 whole square is equal to a square. Therefore, x square plus y square minus 2ax is equal to 0. Equation 1. Differentiating equation 1 with respect to x, we have 2x plus 2y y dash minus 2a is equal to 0. Therefore, 2a is equal to 2x plus 2y y dash. Equation 2. Substitute the value of 2a from equation 2 in equation 1. We get x square plus y square minus x into 2x plus 2y y dash is equal to 0. Therefore, x square plus y square minus 2x square minus 2xy y dash is equal to 0. Therefore, 2xy y dash plus x square is equal to y square, which is the required differential equation. Example 2. Form the differential equation of the family of ellipses having foci on y-axis and center at origin. Solution. Equation of the family of ellipses having foci on y-axis and center at origin is x square upon b square plus y square upon a square is equal to 1. Equation 1. Differentiating equation 1 with respect to x, we have 2x upon b square plus 2y upon a square y dash is equal to 0. Therefore, x upon b square plus y dash upon a square is equal to 0. Equation 2. Again differentiating equation 2 with respect to x, we have 1 upon b square plus 1 upon a square into y double dash plus y dash whole square is equal to 0. Therefore, y dash plus y dash whole square is equal to minus a square upon b square. Equation 3. Equation 2 implies y dash upon a square is equal to minus x upon b square. Therefore, y dash upon x is equal to minus a square upon b square. Substitute this value in equation 3, we get equation 3 implies y double dash plus y dash whole square is equal to y dash upon x. Therefore, x y double dash plus x into y dash whole square is equal to y dash. Therefore, x y double dash plus x into y dash whole square minus y dash is equal to 0, which is the required differential equation. Methods of solving first order first degree differential equations. In this section, we shall discuss 3 methods of solving first order first degree differential equations. Differential equations with variables separable. A first order first degree differential equation is of the form dy by dx is equal to f of x, y. Equation 1. If f of x, y can be expressed as a product g of x into h of y, where g of x is a function of x and h of y is a function of y, then the differential equation 1 is said to be of variable separable type. The differential equation 1 then has the form dy by dx is equal to g of x into h of y. Equation 2. If h of y is not equal to 0, separating the variables, 2 can be rewritten as 1 upon h of y dy is equal to g of x dx. Equation 3. Integrating both sides of equation 3, we get integration 1 upon h of y dy is equal to integration g of x dx. Equation 4. Thus, equation 4 provides the solutions of given differential equation in the form h of y is equal to g of x plus c. Here, h of y and g of x are the antiderivatives of 1 upon h of y and g of x respectively, and c is the arbitrary constant. Example 1. Find the general solution of the differential equation dy by dx is equal to 1 minus cos x upon 1 plus cos x. Solution: dy by dx is equal to 1 minus cos x upon 1 plus cos x. Therefore, dy by dx is equal to 2 sin square x by 2 upon 2 cos square x by 2. Therefore, dy by dx is equal to tan square x by 2. Equation 1. Separating the variables, equation 1 can be written as dy is equal to tan square x by 2 into dx. Integrating both sides, we get integration dy is equal to integration tan square x by 2 into dx. Therefore, integration dy is equal to integration sec square x by 2 minus 1 into dx. Therefore, y is equal to 2 tan x by 2 minus x plus c, which is the required general solution. Example 2. Find a particular solution satisfying the given condition of the differential equation cos dy by dx is equal to a, where a belongs to R, y is equal to 2 when x is equal to 0. Solution: cos dy by dx is equal to a. Therefore, dy by dx is equal to cos inverse a. Therefore, dy is equal to cos inverse a into dx. Integrating both sides, we have integration dy is equal to cos inverse a into integration dx. Therefore, y is equal to cos inverse a into x plus c. Now, y is equal to 2 when x is equal to 0. Therefore, 2 is equal to 0 plus c implies c is equal to 2. Therefore, the required particular solution is y is equal to x into cos inverse a plus 2. Therefore, y minus 2 upon x is equal to cos inverse a. Therefore, cos y minus 2 upon x is equal to a. Example 3. In a bank, principal increases continuously at the rate of r% per year. Find the value of r if rupees 100 double itself in 10 years, where log of 2 to base e is equal to 0.6931. Solution: let the principal at time t is p. Given that principal increases continuously at the rate of r%, therefore dp by dt is equal to r upon 100 into p. Therefore dp by p is equal to r upon 100 dt. Integrating both sides, we have integration dp by p is equal to integration r upon 100 dt. Therefore, log of modulus p is equal to r upon 100 into t plus c. Therefore, t is equal to 0 when p is equal to rupees 100. Log is equal to 100 is equal to 0 plus c implies c is equal to log 100. Therefore, log p is equal to rt upon 100 plus log 100. T is equal to 10 years, p is equal to rupees 200. Log 200 is equal to r into 10 upon 10 plus log 100. Therefore, log 200 minus log 100 is equal to r upon 10. Therefore, log 2 into 10 is equal to r. Therefore, r is equal to 0.6931 into 10. Therefore, r is equal to 6.931. Homogeneous differential equations. Consider the following functions in x and y. f1 of xy is equal to y square plus 2xy. f2 of xy is equal to 2x minus 3y. f3 of xy is equal to cos y upon x. f4 of xy is equal to sin x plus cos y. If we replace x and y by lambda x and lambda y respectively in the above functions for any non-zero constant lambda, we get f1 of lambda x lambda y is equal to lambda square into y square plus 2xy is equal to lambda square f1 of xy. f2 of lambda x lambda y is equal to lambda into 2x minus 3y is equal to lambda f2 of xy. f3 of lambda x lambda y is equal to cos lambda y upon lambda x is equal to cos y upon x is equal to lambda raised to 0 f3 of xy. f4 of lambda x lambda y is equal to sin lambda x plus cos lambda y is not equal to lambda n f4 of xy for any n belongs to n. Here we observe that the functions f1, f2, f3 can be written in the form f of lambda x lambda y is equal to lambda raised to n f of xy, but f4 cannot be written in this form. This leads to the following definition. A function f of xy is said to be homogeneous function of degree n if f of lambda x lambda y is equal to lambda raised to n f of xy for any non-zero constant lambda. We note that in the above examples, f1, f2, f3 are homogeneous functions of degree 2, 1, 0 respectively, but f4 is not a homogeneous function. We also observe that f1 of xy is equal to x square into y square upon x square plus 2y upon x is equal to x square h1 of y upon x, or f1 of xy is equal to y square into 1 plus 2x upon y is equal to y square h2 of x upon y. f2 of xy is equal to x raised to 1 into 2 minus 3y upon x is equal to x raised to 1 h3 of y upon x, or f2 of xy is equal to y raised to 1 into 2x upon y minus 3 is equal to y raised to 1 h4 of x upon y. f3 of xy is equal to x raised to 0 cos y upon x is equal to x raised to 0 h5 of y upon x. f4 of xy is not equal to x raised to n h6 of y upon x for any n belongs to n. f4 of xy is not equal to y raised to n h7 of xy for any n belongs to n. Therefore, a function f of xy is a homogeneous function of degree n if f of xy is equal to x raised to n g of y upon x or y raised to n h of x upon y. A differential equation of the form dy by dx is equal to f of xy is said to be homogeneous if f of xy is a homogeneous function of degree 0. To solve a homogeneous differential equation of the type dy by dx is equal to f of xy is equal to g of y upon x. Equation 1. We make the substitution y is equal to v into x. Equation 2. Differentiating equation 2 with respect to x, we get dy by dx is equal to v plus x into dv by dx. Equation 3. Substituting the value of dy by dx from equation 3 in equation 1, we get v plus x into dv by dx is equal to g of v or x into dv by dx is equal to g of v minus v. Equation 4. Separating the variables in equation 4, we get dv by g of v minus v is equal to dx by x. Equation 5. Integrating both sides of equation 5, we get integration dv by g of v minus v is equal to integration 1 upon x dx plus c. Equation 6. Equation 6 gives general solution that is primitive of the differential equation 1 when we replace v by y upon x. Example 1. Show that the differential equation y dash is equal to x plus y upon x is homogeneous and solve it. Solution: y dash is equal to x plus y upon x. Therefore, dy by dx is equal to x plus y upon x. Equation 1. Let f of xy is equal to x plus y upon x. Therefore, f of lambda x lambda y is equal to lambda x plus lambda y upon lambda x is equal to lambda into x plus y upon lambda x is equal to lambda raised to 0 f of xy. Thus, f of xy is a homogeneous function of degree 0. Therefore, the given differential equation is a homogeneous differential equation. Suppose that y is equal to v into x. Therefore, dy by dx is equal to v plus x into dv by dx. Substitute this value in equation 1. We get v plus x into dv by dx is equal to x plus vx upon x. Therefore, x into dv by dx is equal to 1 plus v minus v. Therefore, x into dv by dx is equal to 1. Therefore, dv is equal to dx by x. Integrating both sides, we get integration dv is equal to integration dx by x. Therefore, v is equal to log x plus c. Now, replace v is equal to y upon x. Y upon x is equal to log x plus c. Therefore, y is equal to x into log x plus cx. Example 2. Find the particular solution satisfying the given condition. 2xy plus y square minus 2x square dy by dx is equal to 0. Y is equal to 2 when x is equal to 1. Solution: 2xy plus y square minus 2x square dy by dx is equal to 0. Therefore, dy by dx is equal to 2xy plus y square upon 2x square. Equation 1. This is a homogeneous differential equation. Let y upon x is equal to v. Implies y is equal to v into x. Implies dy by dx is equal to v plus x into dv by dx. Substitute this value in equation 1. We have v plus x into dv by dx is equal to 2x square v plus x square v square upon 2x square. Therefore, x into dv by dx is equal to 2v plus v square upon 2 minus v. Therefore, 2 upon v square dv is equal to dx by x. Integrating both sides, we get integration 2 upon v square dv is equal to integration dx by x. Therefore, 2 into minus 1 upon v is equal to log modulus of x plus c. Putting v is equal to y upon x, take minus 2x upon y is equal to log modulus of x plus c. Equation 2. Now, y is equal to 2 when x is equal to 1. Therefore, minus 1 is equal to log 1 plus c implies c is equal to minus 1. Putting the value of c in equation 2, we get minus 2x upon y is equal to log modulus of x minus 1. Therefore, 2x upon y is equal to 1 minus log of modulus x. Therefore, y is equal to 2x upon 1 minus log modulus of x, which is the required differential equation. Linear differential equations. A differential equation of the form dy by dx plus py is equal to q, where p and q are constants or functions of x only, is known as a first order linear differential equation. Some examples of the first order linear equation are dy by dx plus y is equal to sin x, dy by dx plus 1 upon x into y is equal to e raised to x, dy by dx plus y upon x log x is equal to 1 upon x. Another form of first order linear equation is dx by dy plus p1x is equal to q1, where p1 and q1 are constants or functions of y only. Some examples of this type of differential equation are dx by dy plus x is equal to cos y, dx by dy plus minus 2x upon y is equal to y square e raised to minus y. To solve the first order linear differential equation of the type dy by dx plus py is equal to q. Equation 1. Multiply both sides of the equation by a function of x, say g of x. To get g of x dy by dx plus p into g of x into y is equal to q into g of x. Equation 2. Choose g of x in such a way that right hand side becomes a derivative of y into g of x. That is, g of x dy by dx plus p into g of x into y is equal to d by dx y into g of x. Or g of x dy by dx plus p into g of x y is equal to g of x dy by dx plus y into g dash of x, implies p into g of x is equal to g dash of x, or p is equal to g dash of x upon g of x. Integrating both sides with respect to x, we get integration p dx is equal to integration g dash of x upon g of x dx, or integration p dx is equal to log of g of x, or g of x is equal to e raised to integration p dx. On multiplying the equation 1 by g of x is equal to e raised to integration p dx, the left hand side becomes the derivative of some function of x and y. This function g of x is equal to e raised to integration p dx is called integrating factor, that is if, of the given differential equation. Substituting the value of g of x in equation 2, we get e raised to integration p dx dy by dx plus p e raised to integration p dx y is equal to q e raised to integration p dx, or d by dx y e raised to integration p dx is equal to q e raised to integration p dx. Integrating both sides with respect to x, we get y e raised to integration p dx is equal to integration q e raised to integration p dx into dx, or y is equal to e raised to minus integration p dx integration q e raised to integration p dx into dx plus c e raised to minus integration p dx, which is the general solution of the differential equation. Steps involved to solve first order linear differential equation. Number 1. Write the given differential equation in the form dx by dy plus py is equal to q, where p, q are constants or functions of x only. Number 2. Find the integrating factor, that is if, is equal to e raised to integration p dx. Number 3. Write the solution of the given differential equation as y integrating factor is equal to integration q into integrating factor into dx plus c. In case the first order linear differential equation is in the form dx by dy plus p1x is equal to q1, where p1 and q1 are constants or functions of y only, then integrating factor is equal to e raised to integration p1 dy. Solution of the differential equation is given by x into integrating factor is equal to integration q1 into integrating factor into dy plus c. Example 1. Find the general solution of the differential equation dy by dx plus 3y is equal to e raised to minus 2x. Solution: dy by dx plus 3y is equal to e raised to minus 2x. Equation 1. This is a linear differential equation of the type dy by dx plus py is equal to q, where p is equal to 3 and q is equal to e raised to minus 2x. Integral factor is equal to if is equal to e raised to integration p dx is equal to e raised to integration 3 dx is equal to e raised to 3x. Multiply equation 1 by e raised to 3x. We have e raised to 3x dy by dx plus 3 e raised to 3x into y is equal to e raised to 3x into e raised to minus 2x. Therefore, d by dx y into e raised to 3x is equal to e raised to x. Integrating both sides with respect to x, we get y into e raised to 3x into y is equal to integration e raised to x dx. Therefore, y into e raised to 3x is equal to e raised to x plus c. Therefore, y is equal to e raised to minus 2x plus c e raised to minus 3x, which is a general solution of the given differential equation. Example 2. Find the equation of a curve passing through the point 0, 1. If the slope of the tangent to the curve at any point x, y is equal to the sum of the x coordinate, that is abscissa, and the product of the x coordinate and y coordinate, that is ordinate, of that point. Solution: we know that the slope of the tangent to the curve is dy by dx. Therefore, dy by dx is equal to x plus xy, or dy by dx minus xy is equal to x. Equation 1. This is a linear differential equation of the type dy by dx plus py is equal to q, where p is equal to minus x and q is equal to x. Therefore, integral factor is equal to e raised to minus x dx is equal to e raised to minus x squared by 2. Hence, the solution of equation is given by y e raised to minus x squared by 2 is equal to integration x into e raised to x squared by 2 into dx plus c. Equation 2. Let I is equal to integration e raised to minus x squared by 2 dx. Let minus x squared by 2 is equal to t. Then minus x dx is equal to dt, or x dx is equal to minus dt. Therefore, I is equal to minus integration e raised to t dt is equal to minus e raised to t is equal to minus e raised to minus x squared by 2. Substituting the value of I in equation 2, we get y e raised to minus x squared by 2 is equal to minus e raised to minus x square by 2 plus c. Therefore, y is equal to minus 1 plus c e raised to x square by 2. Equation 3. Now, equation 3 represents the equation of family of curves. But we are interested in finding a particular member of the family passing through 0, 1. Substituting x is equal to 0 and y is equal to 1 in equation 3, we get 1 is equal to minus 1 plus c into e raised to 0 or c is equal to 2. Substituting the value of c in equation 3, we get y is equal to minus 1 plus 2 e raised to x square by 2, which is the equation of the required curve.